Okay, so hello everyone. Welcome to day 5 on programming with Sycl. First of all, I want to tell you guys that today is your last lecture because we are busy, so we will not be available to take class on tomorrow. So this is going to be our last lecture on programming with Sycl. Today we will wrap up the course. Yeah. Okay, let's start today's lecture. Let the people join with time. Okay, let's begin. So today's topic is kernel reduction. Okay, then we will see some advanced topic in accessors and buffers. We will see sub-buffers, dependencies when using buffers and accessors, and then we will jump onto the graph representation. Uh, Graph in GPUs, how we can get better performance for the graphs in GPU. We will see data-driven versus topology-driven, and then we will see how we can parallelize the BFS code using GPU with the help of BFS, and how we can write the single source shortest path algorithm. Okay, so moving on to the first topic of today, kernel reduction. So what does reduction do in Sycl? So a reduction produces a single value by combining multiple values in an unspecified order. Uh, and the operator should be both associative and commutative. Sorry for the background noise. Yeah, so the operator should be both associative and commutative, like addition and multiplication. And in reduction, only the final value resulting from reduction is of interest to the programmer. So we don't need the sub in between values, like while doing sum of all the arrays, all the values of array, we don't need the sum in between. We will only need the final sum, that is after summing all the values of that array. So only the final value resulting from reduction is of interest to the programmer. So sometimes parallelizing reduction can be very tricky because the nature of computation and accelerator hardware. And so let's move on to the code, how we can use reduction. So mm, here we can see that reduction can be performed on GPU using kernel invocations, either using single task or parallel for. Okay, so here the code that I am showing is reduction with single task, and this is the simplest way actually to write a kernel function to compute sum for GPU using kernel invocations using single task. We can do it also using parallel, using for loop to compute the sum of all values in the array. So, but this way of reduction works, but there is no parallelism involved. Okay, anywhere. If we want to do this type of reduction using single thread of GPU, then we better do it in the host part that is on the CPU, because while if we compare the speed of one thread of CPU to the one thread of GPU, and CPU threads are much faster in comparison to GPU threads, but it's why we are but why the overall efficiency, the computation in GPUs are much faster, because the number of threads in GPU are much higher. It's in approximately in millions number of threads are in GPU, while in CPU you will get a few hundreds of threads. Uh, as we also know that there are some multi-threading concept in CPU also, but with the help, but with those also, you won't get that much efficiency. That's why people have made separate hardware like GPU. Now, let's move on to the reduction in parallel for USM. Okay. So, wait for a second. Yeah. So, Sycl introduces a reduction to the anti-range version of a parallel for. So, first, let me tell you what does that anti-range means. I expect that you guys should have known after the yesterday's class. So, N represents the global size. Here, what it has written, N and B. So, I'm explaining that. So here, N represents the global size of the range of work item. That is, if you have 1024 elements in total in the array, then N is representing that. Okay, so N basically includes the total number of work item that will be created for execution. So basically, if you have 1024 elements in the array, then 1024 threads will be made or will be called. Okay, so this typically refers to the overall size of the data that is being processed by the parallel operation, that is N equal to N. And now, what is B? So B denotes the local size or work group size, which specifies the number of work item in a work group. So this 120, so this 1024 gets divided into chunks of 128, 128, 128. Okay. So work groups are logical sets of work item that are executed together. So work groups are logical sets of work item means that these 128 are these 128 means there are 128 threads in it. Okay. So and this the local size determine the number of work items that collaborate and synchronize within a work group during execution. Now let's just go line by line, in the code. So the first Q dot parallel for entering something is written. Okay, here I'm telling you Q dot parallel for anti range reduction, a long line. So this line, what this does is this line initiates a parallel computing using the parallel for function, and it specifies a range of work item to be processed with the help of this anti range 1 and B. Again, the 1 represents the dimension of the array or the buffer. Then Sycl reduction run Sycl plus something is written. So here sum is the variable to be reduced, and Sycl plus is the reduction operator, and that is representing the basically that we have to, it's representing that we have to do the addition operation. So the reduction objects encapsulates the sum variable and the reduction operator, allowing the reduction to be performed across all work items, that is across all threads. After that, it is simple. Int I equal to this auto I equal to it dot get global ID 0 temp dot combine data I. So what this two line means, each work item access the global ID and combines the corresponding data element, that is data file, with the reduction variable temp using the specified reduction operator. So basically, we are just calculating the sum of that array. Here we have initialized that array in the host part, and this is for the entire thing. Here it is written for computing the sum of that array in parallel using reduction. Some same thing we have. Okay, this is notification keep happening. Guys, tell me if anyone request for admit permission, because I can't see. I have to switch the tabs again and again. Now let's see a reduction in parallel for buffers. Uh, in the previous code, we were not using any accessor or buffer, but here we are using buffer and accessor. So uh, just because we have used here uh, malloc shared memory, that's why, because when we use malloc shared memory, so it is accessible on both host and device. Therefore, we can write that directly over here. But here in this code, once we make buffer for the once we make buffer for any data, then we will have to make accessor for it, and then you will have to accessor for manipulating that data. Okay. So here you have made first initialize the vector over here in the host part. Then you have made buffer for that, and you have made an int sum equal to 0, an integer sum 0 variable, and you also have to make buffer for that also, because you have made int sum. You have initialized that in the host. So you have made two buffers, and then you have made accessor for data. Now here, instead of writing sum, that sum here the sum is declared as shared, so we can write directly over here. But since we have made buffer over here, we will have to write buffer sum. Why we are not using accessor for buffer sum? Because we are not using anything related to buffer sum over here. Here we are just using accessor data file. So that's why when accessor is using when accessor is using the buffer data, then only it gets to know that I have to copy the entire data of buffer into the device. Okay. So this buff sum. So after okay. So one thing to note here is that I have used here curly braces. So once we come out of this curly braces, this buffers get destroyed. And once the buffer gets destroyed, its updated values get copied in these vector and this sum variable. Okay, the data buff data gets copied over here if it has updated, and the sum also gets updated over in the sum variable. So after this, after coming out of from the curly braces, we can print its updated value in the host. Now moving on to the next slide. So here we can see that we have used multiple reductions. Here we are not only here we have not only used sum, but also used buffer minimum, buffer maximum. Okay. So let's see line by line what's happening over here. Firstly, we have a vector data of size n, which is created and initialized with integer values. Then we have a buffer creation. We have made 4 buffers: buffer data, sum, minimum, and maximum, which are created to store the data, sum, minimum, and maximum values respectively. Then there is queue summation and kernel summation. Sycl, in all the Sycl program, a Sycl queue is used to submit tasks within this scope. A command group is submitted to the queue. So here is this all we can call as command group. Okay. Now the reduction object. One thing to note over here is that instead of writing reduction buffer sum h plus over here, okay, what we have done, we have made an object named reduction sum, so that otherwise it will get messy. So we have stored that in an object, and now we are writing it over here: reduction sum, reduction min, reduction max. Otherwise, what we have to do, we have to write the entire reduction of sum h plus over here, like we did in the previous code. We have write the whole part over here. Otherwise, we could have just done auto reduction sum equal to this, and we just write the reduction sum over here. That will also go slow. So just like we get the sum of all the array values, we can also get the minimum element of that array and maximum element of that array by using reduction. Okay, now, is there any doubt in this slide? If someone wanna ask any doubt. So I again repeat that this is going to be the last lecture on programming with Sycl. We will be busy tomorrow, so none of us are available. That's why we'll have to end our course today. Okay, if there's no doubt, let's move ahead. So now let's explore buffer and accessors in depth. Okay, before moving to the let me quickly revise you what was the buffer and accessors that we have discussed 2 days before. So buffers are a high-level abstraction for data, and these are accessible either on the host machine or on the device. Buffer encapsulates data in a Sycl application across both host and the device. And we use accessor. That is, accessor is the mechanism to access buffer data. And buffer can be of one-dimensional, two-dimensional, or three-dimensional. Okay, and one of the most important aspects of data parallel computation is how they access data to accelerate the computation. Accelerator device have their own attached memories that can not be directly accessed from the host. Okay, so device and host can either share physical memory. Okay, sorry for the disturbance. Wait a minute. There were some monkeys. Yeah, so accelerator device have their own attached memories that cannot be directly accessed from the host. And device and host can either share physical memory or can have distinct memories. When the memories are distinct, offloading computation requires copying data between host and device. And obviously, Sycl does not require you to manage the data copies. How? By creating buffers and accessors. That is, the Sycl ensures data is available to host and device without any effort on your part. And buffers and accessor also allows you explicit control over data movement to achieve the best performance. Uh, Also, there is some USM unified shared memory. So USM, what USM does, USM forces programmers to think about when memory lives and what should be where. The buffer abstraction is a high-level model that hides this from the programmer. Otherwise, when you use USM, you will have to explicitly copy the data from device to host and host to device. But when you use buffers and accessors, it's just abstracted. So it provides you a abstraction. It's taken care of by them only. So while buffers abstract how we represent and store data in a program, we do not directly access the data using the buffer. That is, instead we use accessor objects that inform the runtime how we intend to use the data that we are accessing through buffers. Now let's come on to how we can create buffers. So here the buffer class is a template class. I hope you guys know what is template class. If not, you can go and study about it. It's let me tell you in brief. What happens is that suppose there is a template class, template function, template arguments. So suppose if we take example of template function. So you made a function to swap two values. So if in general you can make a swap function that can swap any two numbers, be it any bit of any data type like integer, float, double. Okay, so when you generalize this, you can call it as a template function. Okay. So the buffer class is a template class with three template arguments. The first argument is the type of object that the buffer will contain. The type of object means whether it is array, vector, okay. The basically, or we can say the data type also. The second template argument is an integer describing the dimensionality of the buffer. That is easier to understand. It's a one dimensional, two dimensional. All the single data type like int, float, it will count as one. Now the final template optional arguably is usually the default value. Okay, so default. Okay, let me read it. The final value is the default value. So it means that you will use it while if you want to perform any memory allocation on the host. Okay. So if we want to, generally what happens is that when we make buffer, so the moment that we make buffer, memory is not allocated to the buffer, and we make accessor for it, and the accessor tries to use the uh, data from the buffer at that time. At that runtime, compiler gets to know that it is accessing the buffer values. So at that time, the values get copied to the buffer. But if you want to if you want to initialize buffer while making it, then that also you can do it with the help of that final template optional argument. So let's move again. Let's move to the next slide. So here we can see that I have created three buffers. I have shown you how we can create a buffer. So they have made buffer. They are all out of different types. I mean, they've been made by three different types. So let's come on to the buffer one. So we can initialize one-dimensional buffer using containers in two different ways. First, if the container object that provides the initial value for a buffer is also contiguous, it means that my vector is contiguous. So if you want to allocate memory for that, like if there is if the vector size is from 0 to 500, then it is contiguous. Then if you want to make buffer to copy those data from 0 to 500, then simply you can write buffer b1 and my vector. The whole things get copied. Similarly, if you don't want to copy the entire vector, what you can do, you can just mention from address from where you want to start and from where you want to end, so the buffer will copy only that much amount of data for you. Now, now the size of the buffer is the size of the container used to initialize it, and the type for the buffer data is the type of the container data. Okay, that I just told you about it. Let's talk about the buffer tree. So here buffer tree creates a one-dimensional buffer for four double values. Okay, how we have done that? How we have made it? We pass the host pointer to the C++ array my doubles to the buffer constructor in addition to the range that specifies the size of the buffer. That is, we have mentioned that 4. Okay, this tells the size of the buffer. So by passing a pointer to the host memory, we also need to make sure we should not try to access the host memory during the lifetime of the buffer to avoid any data risk condition. That is, once you have created buffer for any vector or array, then you can only access those values using buffer only. And if you till the buffer is alive, once the buffer gets destroyed, then automatically the data gets copied back into the original memory of host. So these are the three types. Let's move to the next slide. So here, no init. So no init, I have used that in accessors. So first of all, let's quickly revise what is accessor. So data represented by buffer cannot be directly accessed. Okay, we have learned that already. Cannot be directly accessed through the buffer object. Instead, we must create accessor objects that allows to safely access a buffer data. And accessors inform the runtime where and how we want to access those data. Uh, that allows the runtime to ensure that the right data is in the right place at the right time, and the kernel don't run until all the data is available to the accessor. So there are basically three type of access modes. One is read only, one is write only, and third one is read write. Okay, so when creating accessors, we must inform the runtime how we are going to use it by specifying an access mode that I just told you. Read only, write only, or read write. So access modes are how the runtime is able to perform implicit data movement. When accessor is created, suppose like when accessor is created using a read write, we intend to both read and write to the buffer through the accessor. And sorry. Huh? Someone was at the door. Yeah, so we have to make sure that whenever we are using read only, it tells the runtime that the data needs to be available on the device before the kernel can begin executing anything. Okay. So similarly, write only lets the runtime know that we will modify the contents of a buffer and may need to copy the results back after the computation has ended. So what is the no init no init past and all and that we as an optional accessor property. A property we pass the previous content of the buffer can be discarded. Uh, no init property is useful because it can the property is useful because it can let runtime eliminate any data. Like in this example, uh, is the first task is writing the initial buffer. So, so it's unnecessary for them to copy the initial line number to the device before the use. So, am I audible, guys? Hello, am I audible? Am I audible? Hello. Can you write in chat yes or no? Hello. Am I audible? Okay. Thanks. So sorry, I got disconnected. So I was talking about the no init function. So here, as we see that we have initialized the buffer, and we are initializing. We have made buffer over here, and we are initializing that we are updating its value in the parallel for function. So obviously, when we write read only here, what it will does that it will copy the buffer data in the device. But we don't need that because right now it has garbage values that we don't need to copy. So so it's better to write only here. That's why we have written a no in it, so that the compiler will get to know that it don't need to copy those uninitialized values when we made accessor. And also just keep in mind that this no init property is useful for this example, but it should not be used for read, modify, write cases or kernels where only some values in buffer may be updated. Okay. So what it is saying that here we are updating every value. That's why we can use no init property. If there are some previous values that we don't want to change or we want to keep it, then obviously we cannot use no init function because then what happened is that we might lost that value that may be of use in the future. So so in the last class, I told you guys that host accessor is a blocking call, and we use host accessor. So when we come out of these q dot submit, so with the help of host accessor, we can print the buffer values in the host. But what we can also do is that with the help of host accessor, we can initialize the buffer. It's just an idea that how we can use the host accessor. So here I have created buffer directly using, and then I have made a host accessor within this scope. And with the use of host accessor, I am initializing the buffer values of both in buffer and out buffer. So it's just an idea that you can use the host accessor in two ways. Now coming on to the next topic, sub buffer. So the main advantage of using the sub buffer is since the sub buffers, what is sub buffer? When we make buffer of buffers that we call as sub buffer. So the advantage of using the sub buffer is since the sub buffers do not overlap, different kernels operate on different sub buffers concurrently. Let's see how. Suppose there are 10 elements in a buffer. Then what we can do, we can make two separate buffers of five integers. And then if we want to perform some computation, we can perform on those two buffers parallelly. Let's see a code that you guys will get better understanding of it. So what I have done over here, I have declared n as 64. There is there are two integers, num1 and num2, whose values are 2 and 3 respectively. Then I made an integer array. I have initialized that in the host part, and then I have made a buffer for that array. Now I created sub buffers. That is, I have made first buffer for this array, and then I have made two buffers for this already made buffer. So this buffer B1 and B2, uh, what they will point to this buffer B. So buffer B have 64 elements. So buffer B has 64 elements in it, and buffer B1 and buffer B2 have range n by 2 n by 2. It means 64 by 2, that is equal to 32 elements in them. And here we are passing the starting address. Okay, so buffer B1 will point to 0 to 31 index. That is from 0 to 31 is total 32 elements. And similarly, buffer B2 will point to from index 32 to 63. So in total, there are 32 elements that they are pointing out to. Now, what I have done over here, I have made two queues, the Q1 and here I have made Q2. So since I have made two separate queues, both of the queues can, uh, these queues can run parallelly. Here I am, what I am doing over here in the Q1, I am changing the values from index 0 to 31 by multiplying every value by num1, that is 2. And from 32 to 63 index, I am just multiplying it with number 3. So both of them are happening parallelly. Now, once I come out of this Q2, I can make host accessor, and I can make host accessor for buffer B1 and B2. Yeah, that is a good point. That I can make a host accessor for this sub buffers also. Okay, so I have made a host accessor for sub buffers, and then I am printing those values in the host. Now, so I will get the updated value. So the computation becomes 2 times faster. Now, moving on to the next slide. Here, there are generally two type of dependencies. One is linear dependency, and one is a Y-shaped dependency. That I will tell you in the next slide. Here, the linear dependency. What does it mean? That I have made a buffer data. So, and for this buffer data, I have made accessor, and with the help of accessor, I am manipulating the values in that buffer. So, so once this gets completed, then only I can come to these queue. Why? Because first I have used the I have here made only one queue. So both of them cannot run parallelly. They can run parallelly only when I will make Q1 and then I will make Q2. Okay, so they cannot run parallelly. They will run sequentially, one by one. So once it will get complete first, then only I can come to here, and that is good because I am using the updated whatever the changes that I have made here. I have to use that here. So this is a linear dependency. That this is dependent on whatever changes I have made it over here. Okay. And now this Y shape pattern. Why I'm calling this? Because suppose there is one kernel and there is second kernel. So here the kernel, here the third kernel depends on what changes has been made on 1 and 2. So the kernel 3 depends on the kernel 1 and 2. Okay. So here I have made two buffers, the Y shape. We are learning the Y shape dependency. So here I have made two buffers for data one, data named as data one, data two. Both have 42 integers in them initially. Then with this help of Q, I am initializing it. So both of them can be done in the same for loop. I don't need to make a kernel over here. Okay. what I could have done, I could have just copy pasted it over here so that both have same both are indexing from 0 to 41. So that could have been done. That could have been merged together. And in the third kernel, I am using whatever changes I have made in Q, this kernel 1 and kernel 2. So there is dependency. In the last class, what I told that both these will run parallelly. No, that was wrong. Actually, they can run parallelly only when if it is different queue and it is different queue. Then only they can run parallelly. Okay. If you are making single queue and submitting tasks to it, then they are going to run in sequential. So this is a Y-shaped pattern dependency. Now here is a homework for you. Task scheduling and task scheduling data dependency. I want you guys to think about it, write the code, take it as a homework. Okay, I'm giving you 5 minutes to think on it, and then either you can put the code in chat, just the pseudo code type of think about this, how you can implement it. So what we have to do over here is that they first they are asking us to create three vectors, okay, data 1, data 2, and data 3, which are and they are asking us to initialize them on the host, and that is easy part. Either you can initialize using after they have asked us to do that using making buffers and accessors. So what we will have to do, we'll have to make a host accessor, and after making host accessor, we have to initialize it on the on after yeah after making host accessor, you will have to initialize it in a scope. Then we have to firstly we have to create buffers, and then only we can initialize it. Then it is saying that we have to update data 1 by adding data 1 and data 3, and then it is saying we have to multiply data 2 by multiplying it by 2. So note that there is no dependency involved over here. Okay, so both of them can be run in single s.parallel for. Given that both of them have same number of elements in them, data 1, data 3, and if data 2 both have same n number of elements in it. So since there are no dependency in it, then these two tasks can be done together. Okay, we can do it in single s.parallel for. After that, we can after that, once both these tasks are done, we can update the data 3 to data 1 plus data 2 plus data 3. And you guys can read this. This is easy to implement. I hope you will be able to do it. Okay. Is there any question regarding this? Uh, If no, then we will move to the graphs. That will be the last topic which we will be covering. Okay, if there is no doubt, let's move ahead. Okay, so let's start graphs. So where do we encounter graph? Everywhere. So social network, road connections, molecular interactions. Okay. Why we treat them separately? Because they provide some structural information, and they can be processed much more efficiently using GPU. But uh, they also pose some challenges, because if there are 1,000 nodes in a graph, then not all the nodes have same amount of work to be done. There can be load imbalance, poor locality, that we say. So graphs are everywhere. So why we are learning it? Because using a GPU for graph processing can be beneficial, can be very beneficial actually, due to the inherent parallelism involved, due to the inherent parallelism provided by the GPU architecture. Graph algorithm can offer, and also graph algorithm often involve a processing large amount of data and performing complex computations on graph structure, which can be accelerated by the parallel processing capabilities of GPU. And some very common tasks related to graph processing that can be efficiently executed on GPUs include, obviously, the first one is the graph traversal. The BFS or the DFS can be parallelized effectively. I won't say DFS because DFS are inherently sequential. So it's, and even DFS is using what? DFS is using recursion. And as I mentioned you earlier, that in GPU we don't write recursive codes. So yeah, DFS is very hard to parallelize, but BFS we can very efficiently we can parallelize the BFS code. And what else we can do? We can do the graph analytics, sparse matrix operation, parallel processing of some very important graph algorithm, like a strongly connected algorithm, belief propagation, K-code decomposition, vertex cover, and all that you can do very efficiently. So yeah, in the parallel codes, obviously we will face the synchronization issue. Okay, the the most important thing, how we deal with it is going to be challenging. How we deal it is the and any uh, how we remove any difficulties that we are going to learn today using atomics and all. So these are the challenges that we face in graph algorithms: memory latency, thread divergence, uncoalesced memory access. So not getting in too much detail, let's begin with graph representation. So in total, we have a couple of graph representation, but these are generally what we use. The four graph representation techniques that I'm going to tell you. First one is the adjacency matrix. So suppose this is the graph. Zero is connected to 3, 1 is connected to 3, then there is an edge between 0, 4, 4, 5, 4, 2. Okay, so this is a very small graph. So in adjacency matrix, what you will do, you will make a matrix of size equal to number of nodes into number of nodes. So here we have 6 nodes, then we will create a 2D vector of 6 into 6, that is of total 36 elements. And each element ij denotes if there is edge present between 2 nodes or not. This is for 0, this is for 1, this is for second node, this is for third, 4, and 5. Okay, so it is showing, and also just like indexing over here, 0, 1, 2, 3, 4, 5, we have indexes over here 0, 1, 2, 3, 4, 5. So since there is edge between 0 to 3 and 0 to 4, so 0, 1, 2, 3, and 4. So we have marked it as 1, so that when you will traverse across these array, you will get to know that since it is marked as 1, it means that there is edge present between 0 to 3 and similarly 0 to 4 and so on. Now, adjacency list. What is the adjacency list? Here, from 0, it is connected to 0 is connected to 3, 0 is connected to 4. So with all those elements with which 0 is connected to, we'll make a list of it. Okay. So one, like suppose you have 4 is 0, 1, 2, 3. So 3 is connected to 0, 1. Yeah, 3 is connected to 0, 3 is connected to 1. So this is how adjacency list works. Now coming on to the edge list coordinates COO. Here it's very simple. It's just write all the edges. Okay, so there is 0 to 3, so we write 0 to 3. If it is undirected, like in this case, so we write 3 to 0 also. Okay, and similarly, if there is edge from 1 to 3, then we write 1 to 3. Then we can also write 3 to 1. So in total, if there are here 1, 2, 3, 4, 5, 6, 6 edges, then you will write total in total 12 edges. If this is undirected, if it is directed, then you just need to write 6 edges. So coming on to CSR list, what we generally use, what we prefer most in GPU is the compressed sparse row. And why we use it? Because it takes up very less space. It just uses these two arrays. That's it. Now, how it works? Here, as we can see that 0 is connected to 3, 4. Okay, 0 is connected to 3 and 4. Okay, this is, first of all, this is not the name of nodes. So because we don't have anything as 9 over here, so it is not representing the node. Okay, what it is representing is, it is representing the index. So for 0, we are starting from 0th index. Okay, from 0, here it is a separate array, this is a separate array. So 0 is connected to 3 and 4. That is why we have written 3 and 4 over here. Okay, then comes to 1. When it comes to 1, then 1 is connected to 3, 1 is connected to 5. We have write 3 and 5 over here. Then 2 is connected to 4. So 2 is also only connected to 4. Then 3 is connected to 0 and 1. 3 is connected to 0 and 1. Okay, so and just note that this is also sorted 3, 4, 3, 5, 4, 0, 1, 0, 2. So these 3 and 4 are sorted, not we have written 4 and 3. You have to write it in sorted manner. So what this is representing? This is representing the index. Like for 4, it is connected to 0 and 5. So 0, 1, 2, 3, and 4. So 4 is starting at index 7. Okay. Uh, this CSL is something, there is some mistake over here. Let's suppose, let's see add to 2. So 2 is connected to 4 only. So wait a second. So 0, 1, 2. So 0, 1, and 2. 2 is connected to 4. Yeah. So for 2, this is 0, this is 1, and this is 2. So 2 at for 2, we will go to the fourth index. 0, 1, 2, 3, and 4. So we can see that 2's uh, 2's neighbors will start from index 4. Okay, and it is connected to this 4. So we write 4. So this is CSR list. So the important thing about CSR list is the way we store it. It saves memory when dealing with large matrices that have many empty or zero elements in it. Like instead of storing all the elements, it what it does is that it keeps track of the non-zero values and where they are located. And this helps to save space and make it faster to work with this type of matrices, especially when performing calculations or operations on them. This format is commonly used in fields like scientific computing, where handling large and sparse matrices efficiently is important for achieving better performance. Now, coming on to the topological and that data-driven processing. So there are two types of processing. So when we talk about the topology-driven processing, so what does it mean? It's uh, in uh, in this type of approach, the operation, or we can say that the operation or the computation is applied to all the nodes in the graph, even if some of the nodes do not require any work. For example, in Bellman Fold. Okay, if we do Bellman Fold with the help of GPU, then the computation is carried out for all the nodes, regardless of whether there is any meaning work to be done at those nodes. And this approach ensures that every node is considered and processed during the computation. But since it is not fair, because some nodes don't have any work to do, and some nodes might have a lot of work to be done. Okay, so and now the data-driven processing. Data-driven processing is just opposite. In this, the operation is performed at only those nodes where there is actual work to be done. For instance, in the single source shortest path algorithm, the computation is selectively applied to nodes where there is need for processing. Okay, uh, so this the data-driven processing approach focus more on performing computation only on the data that are relevant to the specific task. Okay, thus optimizing the processing effort and resources. So yeah, here you can see that they are applying the follow for all those nodes. The work, even if there are no work for some nodes to be done, then also we will perform the computation for it. Here it's just opposite. That there is no work from them. We don't do any. We don't need to perform any computation for these nodes. So it saves time for. So it saves a lot of time, and we'll get better performance through data driven. But yeah, it is difficult to code also. So data driven is a little bit more complex, and you will have to think about the synchronization issues that we may stuck on. So you will have to deal with all those. Now, data race. What does that mean? So a data race occurs if all of the following have hold. Data race. Uh, let me first tell you what is the data race. Suppose this is x of 0, and out of 100 threads, some 2 or 3 threads are performing this plus plus operation on it. So suppose there are 2 threads that is performing out of 100 threads that that uh, that there is some condition, and that condition evaluates to true for only these 2 threads. So what happens is that if they perform plus plus x0, we need behind the scenes, what happens is that plus plus is done in 3 steps. First load, increment, and then store. So whatever the address is of the x0 will first get into the register R1. Then we will increment that register value, and then the result get copied back to the x0 address. Okay. So these are the 3 steps. But when 2 threads simultaneously perform to plus plus in these address of x0, what can happen is that both of their register R1 and R2 might read. Suppose the initial value of x0 is 0, then both of them read the initial value as 0. They will increment it to their registers 1 and 1, and both of them will write x0, and both of them will finally write the final value as 1. And that is wrong, because the final value should be 2, because through threads are updating the value. So these are the synchronization issues that we may face. So or we can also call this as data race. So the data race occurs if all of the following hold. If there are multiple threads, yeah, there are 2 threads involved in that. There are 2 threads involved over here. Common memory location plus plus x of 0. Yep. And then at least one write. Yep. There is one write plus plus x0. It means we are performing some write operation. And then there is concurrent execution. We are trying to update x plus plus x0 by 2 threads simultaneously. So there is data race, because all these 4 conditions are getting satisfied over here. Okay. So there are some ways to remove it. We will see how. Now, coming on to the traversal technique that we have in graph. One is the DFS, and the other one is the BFS. So as I told you that DFS is very difficult to parallelize because DFS is inherently sequential. It goes, this is how it goes. A will first go to B, then B will go to C will go to E will go to F, and then H, then it will traverse back again. It will come back again, and then you will traverse the other path. So it is not only sequential but recursive only, recursive also. So as I told you that recursive codes we generally don't write uh, GPU codes because it gets very complex. So uh, so since in BFS code we use for loops and all, and there is Q also involved in it, but we can very efficiently parallelize the BFS code. So first of all, let me tell you in brief how the DFS works. So in the first iteration, we are at here A. In the second iteration, we will move up to E, C, and B. Okay. In the next iteration, from C to B, we can reach up to E and F, and then so on. So in the first iteration, A is explored. In the second iteration, D, C, B are explored, and then E, F, and then H, I. So with the help of these, we can also get the minimum distance. Okay. If the edge weights over here are all one, then we can say that the distance from A to I is equal to the number of iterations that we take to reach till I. Okay, if the edge weights are all one. If there are different edge weights, then there will be an issue. Then we will have to think how we can do it. So let's come to one problem. Let's see one problem. Computing the shortest path for the graph. Okay. So suppose this graph is given to us, and from C, we want to compute the shortest path to all of the vertices. So how we will do it? And the edge weights and these edge weights are different. Okay, it's not one equal to one obviously. So some edge weights have been provided to you. So what we can do over here is that from C we will go to B and D, and obviously that will be the shortest path because there are no any edges involved for moving B and E. So in the first iteration we come into here C, and in the second iteration we explored B and D, and the third iteration we can move to A, we can move to D. So we can explore both these. Now see, if we want to update the D's distance, initially the D's distance is infinite. Okay, initially every distance is infinite from C. As we run the algorithm, we will update it. So in the third iteration, we can reach to D via B or via E. Suppose this distance from CBD is lesser, and this CED is larger than these path. Okay, so this one is the shorter one. This is the larger. This is the larger one. So what I want, that I want a B to update the D value. Okay, not E. So if both of them try to change the distance of D, that is, both of them try to update the value of D distance, what will happen? Again, we will face the same issue. Okay, like over if we face. So there might be some inconsistent result that we get, incorrect result that we might get. So we have to make sure that first first either of them will complete, and then the next one will compare the updated value. Suppose from E the distance of D is 100. So okay, we will update the D distance from infinity to 100, and then we will come and see that, oh, it take me only 50 units to reach till D. So we will read the updated value 100 and will write the updated value of D as 50. But how we can do it? Like here, if for this graph, if we run this algorithm, then initially the D distance is infinite. Okay, so what can happen that B and E simultaneously check that these the if condition is true for both of them, and they will try to update this distance. So we might get inconsistent result. Therefore, we will have to use what? Atomic min. So what atomic min will does is it will make sure that if b if b is changing this value, then all the three operations that we have written over here, that all these three operations will be done together for the b, and then only for e this operation will be performed again. So somewhat we can say that there is some sequentiality involved over here. If someone satisfies this condition, that is B and E is satisfying this condition, then only they can come to here, and once they come over here, they are getting logged. One of them will definitely get logged. So if E is performing, then we will have to wait. If E is performing, then we will have to wait. So after atomic, we write the atomic min, we will definitely get the correct result. So here we can write atomic min, atomic add, atomic maximum. There is different kind of atomic operation that we can use. Okay, so I need you guys to try out the shortest path, single source shortest path code. Okay, I will give you the BFS code in the Google group, with the help of which you must be able to write the shortest path, single source shortest path code. In the BFS code, you don't need the atomic min, atomic max operation, but a BFS code will, the what the BFS code generally does, it will just tell you that how many vertices I am reachable if I start from C. So suppose I start from C, I can say that, oh, I am from C, I can reach up to all those vertices. That we will definitely find you out. But for finding out the minimum distance, you will have to do some computation and all. So is there any doubt regarding this? If there is any doubt, you guys can unmute and ask question. Okay, there's no doubt. Okay, so this was the end. And let me tell you again that this was the last class. We will not be able to take class on tomorrow. And thank you for all of you for joining the lecture. And okay, so yeah, I will share the link with you of the BFS code and the slide. You must try out that the shortest single for shortest path code yourself. Okay then. See you. Bye.